Well, good morning, everybody. I'm Mike Weaver, Associate Director of Sigma-HSE UK Limited, and today I want to give a short talk on ATEX and DSEAR. Before we start, ATEX stands for Atmosphere Explosif, the French for explosive atmospheres, and DSEAR is implemented within the UK only, stands for Dangerous Substances, Explosive Atmospheres Regulations. So I'll talk a little bit about the background of the HSE, the Sigma-HSE group. We're a group of companies headquarters in the UK, and we're dedicated to health and safety and the environment. We have three main units, one in India, in Delhi, soon to move to Hyderabad. We have one in the UK, where our main base is, and we have now a unit operating on the East Coast in the USA. Our area of expertise consists of consultancy, testing and training, and we try to bring together our UK, Indian and USA experts so we can provide a global HSE service and cost-effective engineering solutions. Our main test laboratories are based in the UK, and we work to ISO, DSEAR and ASTM individual standards. We also have a small testing laboratory based in India. So technically wise, we have highly qualified engineers, scientists and chemists, experienced professionals overall, and some of us sit on standards committees, so we keep up to date with what is happening in the world of legislation. We work with global industries in diverse sectors such as the pharma, food, chemicals, oil and gas, utility, personal health, and a lot more. We can do dust, gas and vapor, fire and explosion testing. We're very good into looking into electrostatic problems, and we have electrostatic testing equipment. We have an analytical laboratory, and our laboratories work under EN 17025, and we are the only laboratory in the UK that works to that quality accreditation. Our consultancy services, our team here provides specialist technical knowledge for all types of areas of process safety: industrial fire and explosion hazards, electrostatics, PHA, QRA, hazard, HAZOPs, etc. Functional safety, we can look at LOPA, etc. for that. Environmental services, and we do training workshops. This is a public one as a webinar, but we can come to your site, and we'll now be starting soon training workshops, public ones for people to come to. So the outline of the seminar is looking at explosive atmospheres and dust explosions in particular, background to the legislation and the minimum requirements of DSEAR, dust flammability and the test data needed to prove your cases, hazardous area classification, what is the basis of safety that you need to put into your reports, individual assessments such as non-electrical equipment, ignition risk assessments, and other individual ones may be electrostatic hazards and control. So we'll start off with explosive atmospheres and dust explosions. So first thing, we have a fire and explosion. What are the difference between the two? If you look at the picture on the left, the fuel and oxidant are separate. The fire is surrounded by the oxidant, but the two don't mix together. If you look at it in the explosion, then the fuel, the individual particles, say of a dust cloud, mix with the oxygen to form an explosion. So here we have a fire triangle. Most of you should be familiar with this. We have the fuel, the oxidant, and a potential ignition source of suitable energy, and this will produce a fire. Now we need an explosion, and to get the explosion, we need to mix the fuel and the oxidant together, and we need to confine the two. When we get the explosion then, and that's our explosion, different to a fire. So requirements for an explosion, we know we need fuel. We need combustible dusts. We use the Group A-B test to determine are they Group A flammable or Group B non-flammable. If Group B, we stop here. If Group A, we continue. We need to know operating parameters of our process. Temperature is a typical one we need, and we use MIT and LIT, minimum ignition temperature and layer ignition temperature of dust, to decide if the dust is going to ignite or not, or have the potential to ignite. Types of equipment we use, we need to look at it. Is it a blender, silo, mixer, pneumatic conveyor? And one of the things we probably need to look at is the minimum explosive concentration of the dust. Are we working above that? If so, we're within the flammable range. And the particle size. Normally, we say that anything above 500 micron will not ignite. Therefore, is our dust below 500 micron? If it is, how fine is the particles, or are the particles? The finer the material, normally the easier it is to ignite and the larger the explosion. The oxidant. Are we using air? 95% of the time we are. 21% oxygen in air. If we bring it down below 21, can we keep bringing it down till we don't get an explosion? That's the LOC, limiting oxygen concentration. You could be working with halogens. Halogens such as chlorine, bromine, etc. Some of these go from being an inert to being an oxidant under certain circumstances. CO, carbon monoxide, that can be an oxidant as well. You could have CO2 present in your process that can be broken down for CO as well. CO2 as it stands is an inert. And that's what we can use to stop an explosion. Always be aware that if you increase the oxygen above 21%, then you have increased explosion severity. Sometimes extremely large explosions can occur, and they become much more sensitive to ignition. So the ignition source. Well, we know we need an ignition source to make a fire or an explosion, but we need to know that it's effective. So typical ignition sources are things like hot surfaces, flames, smoking and hot work, static electricity, electrical apparatus, mechanical friction and thermite sparks, lightning. Normally you have lightning conductors to prevent that. These first ones we're looking at here are normally the most important that we would assess when we do a report on the potential ignition sources, but there are other ones you can look at. Exothermic reaction and spontaneous combustion. We can look at ultrasonic sound waves. We can look at adiabatic compression and shock waves, stray electric currents, ionizing radiation, visible and high frequency electromagnetic radiation, radio frequency electromagnetic radiation. So there are a few of them, but as I said, the first ones are the big ones that we would look at, the most common ones. We talked about mixing. Can the oxidant and the fuel mix within your operation? Obviously, as you move materials around, especially dust for instance, then the dust can mix with the oxygen. The level of turbulence affects what goes on as well within the explosion. So with the equipment, the ventilation, the operating methods, you need to consider these to see if mixing can occur a lot more efficiently. Particle size affects the surface area and can produce bigger explosions, easier to ignite. You can't determine the effects of particle size by calculation. You must test, and you must know when you get test data, what is the particle size of the product. We look here, we have a 10 millimeter sided square. We have a surface area of 600 square millimeter. We break it up into 8. We break it up here, and again, we've got the same volume, but now we've got double the surface area now, 1,200 square millimeter instead of 600. Confinement. We need to look at the volumes where we're greater than the explosion limits. For dust, it's the MEC. For gases and vapors, it's between the LEL, the lower explosion limit, and the upper explosion limit. The types of places you may consider are silos, storage tanks, pipework, buildings even, enclosed spaces. That's what we're looking at. Is the fuel confined within a closed space? Combustible dust explosion. This is an example for you. I like the confidence of the man there. We had a small blowback, 2 men blown completely off their feet, and they could have been seriously burnt. I like his confidence. Secondary dust explosions. That was the explosion out in the air. If this was in a confined vessel, then the confined vessel could damage, break, and release the pressure out in a blast wave. This means dust accumulations around can get blown into the air. The fire will then follow the flame, and then it will ignite the secondary dust cloud, and then you will get a secondary explosion. The thing to remember here is the initial explosion is localized within the vessel. Then the flame comes out, shock waves cause further dust dispersion. The secondary explosion can be a much higher overpressure, sometimes twice the initial pressure. So if you've got 8 bar on your material for Pmax, you end up with 16 bar on the secondary explosion. A typical example here from 2008 of how dust explosions were not controlled properly is the Imperial Sugar explosion in Georgia, USA, resulting in 14 deaths, 38 injuries, 14 with life-threatening burns. The explosion was fueled by a simple material, sugar. They had no form of isolation throughout. dust accumulations all over the building. This meant the explosion propagated throughout the building. Failure to understand the basis of safety. And here's some of the pictures you see of the devastation caused by sugar. So we've looked a bit at the fire and explosions. Now we need to know what has Europe tried to put in place to prevent these happening. So I'll give you a bit of a background to legislation and the minimum requirements for DSEAR. So for equipment, we've got a directive in place to facilitate free trade. And this is what they tell you. The idea is if your equipment complies with this directive, you can free trade it within Europe, including the UK. It was aimed at equipment manufacturers. It's called ATEX 114, official title 2014/34 EU. And the original one was 94.9, and you can see that came actually into force in 1994. So it's been around for a very long time. The ATEX 114 came into effect in 2016. So again, it's still been in for 6 years now. Then we have the workers' protection. These are directives aimed at improving the safety in the workplace, and these are focused on employers. You have the Framework Directive 89391 EEC. You can see that's been around for 30+ years. And the Framework Directive covers every type of safety directive in it, including those for fires and explosions. The two we're interested in here are the Chemical Agents Directive 9824 EC, the one I call the Forgotten Directive, because whenever we talk about assessments, we talk about ATEX assessments, whereas in a lot of instances, they're actually CAD assessments that you have to do. Very similar, but people fail to mention this directive. And then we have ATEX 153. This is the one that everybody knows as the ATEX directive. So this is 1999-92 EC. It replaces ATEX 137. Let's have a look at the equipment directive. This is on equipment and protective systems intended for use in potentially explosive atmospheres. Comes under the new legislative framework. It means it's a more simple type of directive, so it's easier to understand. Came into force on April the 20th, 2016, commonly referred to in Europe and within the UK is the Equipment and Protective Systems Intended for Use in Potentially Explosive Atmospheres Regulations 1996, the EPS regulations as they're known. Directive 1949 was last updated in 2005. So what does this cover? It applies to equipment and protective systems intended for use in potentially explosive atmospheres. But it also covers safety devices, controlling devices, and regulating devices which are located outside of explosive atmospheres, but they have a direct impact of what goes on within the explosive atmosphere. And the bottom line is any equipment conforming to ATEX 114 must be allowed on the market in the EU. So what is an explosive atmosphere? Well, if we look at the definition in ATEX 153, it says a mixture with air. Now take that in consideration, it's air. Under atmospheric conditions, it doesn't mean elevated temperature or pressure, it means atmospheric conditions. And then you remember back to what I said about the Chemical Agents Directive. We'll talk about that in a minute. So the flammable substances can be in the form of gases, vapors, mists, or dust. in which after an ignition has occurred, combustion spreads to the entire unburnt mixture. And a potentially explosive atmosphere is an atmosphere that could become explosive due to local or operational conditions. So what is equipment? Equipment can be any types of machine that you're using within your process, any types of apparatus you may have there. They could be fixed or mobile, and they could be the control components and the instrumentation. The sign there shows you that these are equipment which is designed to be used in potentially explosive atmospheres. So these equipment are intended for the generation, transfer, storage, measurement, control, and conversion of energy when processing material. And they're capable of causing an explosion through their own potential source of ignition. The categories here, Group 1 is mining, so we don't normally deal with that one. 99.9% of all we deal with within Europe is surface industry, which will classify it as Group 2. And we have 3 categories here. Category 1, the highest level of protection. We have Category 2, a high level of protection. In Category 3, a normal level of protection. We'll talk about the forgotten directive now, Chemical Agents Directive. This is on the protection of the safety and health of workers from the risks related to chemical agents at work. So this could be anything from washing up liquid, hydrofluoric acid, or any type of flammable material. We talked about the Framework Directive earlier, 89391. This is the 14th individual directive within the meaning of that directive. So what does it cover? Considered hazardous chemical agents. These can be an element or a compound, on their own or admixed, in a natural state, or you could produce them. You could be used or released, including release as waste. How many times do I go on site and people say to me, I say to them, have you covered that under your ATEX and your DSEAR? And they say, well, it's only waste. It's the same material that you're looking at for your protection, and it can kill you just as easy as the initial product that you're making. You need to look at it, whether it is made intentionally or not, and whether you place it on the market or not. In other words, you could have a material which is part of the process for manufacturing a final product. It doesn't actually go to market, but you still need to consider it under ATEX and the Chemical Agents Directive. The main focus of the directive is occupational exposure, but you have to do a risk assessment, and documentation is required under ATEX and DSEAR. As well as occupational explosion, CLAD also covers fires and explosions in chemically unstable substances and also mixtures of them. Refers to ATEX 114 on equipment group categorization and overlaps with ATEX 153 for explosions. It tells you measures must be in place to prevent hazardous concentrations or quantities, avoid ignition sources or adverse conditions for chemically unstable substances. This is where chemical reaction hazards come in. And to mitigate the detrimental effects of fires and explosions and harmful physical effects from unstable substances. So as you can see, CAD is quite prolific in what it covers. ATEX 153 is very specific. It's on the minimum requirements for improving the safety and health and protection of workers potentially at risk from explosive atmospheres. Again, the Framework Directive, 15th individual directive. CAD was 14, ATEX 15. So what are the employer's obligation? They should take organization and/or technical measures in order of priority. Remember what I said with CAD. To prevent the formation of explosive atmospheres, where you can't do that, then avoid ignition of the explosive atmospheres. Mitigate the detrimental effects of an explosion so as to ensure the health and safety of workers. We saw there with the Georgia sugar explosion, this wasn't done. Where necessary, these measures shall be combined and/or supplemented with measures to prevent the propagation of explosion. The word there is isolation. And again, with the sugar refinery, this wasn't done. So the most important thing we need to do is an explosion risk assessment. The employer shall assess the specific risks from explosive atmospheres, taking into account at least the likelihood that explosive atmosphere will occur and their persistence. You could take this as hazardous area classification. The likelihood that ignition sources, and they actually mention electrostatic discharges, will be present and become active, and most importantly, can they become effective? You look at the installations that you've got, the substances used. So this is what I say to people. You can't tell how a material is at risk if you don't know what it needs to ignite it. You don't know what damage is going to be caused unless you know the explosion violence. This must be combined with the processes and their possible interactions. And you must look at the scale of the anticipated effects and make sure they're minimized. The explosion risks shall be assessed overall. Places which are or can be connected via openings to places in which explosive atmosphere may be present shall be taken into account. So connection pipes, etc., to other vessels, you must look into this to stop this happening. So in summary, for ATEX and CAD, ATEX only covers explosive atmospheres. CAD covers hazardous chemical agents, including those giving rise to explosive mixtures. For explosive atmospheres, both directives apply, but ATEX is more specific in its requirement. For all other fires and explosions, CAD applies, including explosive mixtures outside atmospheric range. In other words, oxygen concentration, pressure, and temperature. How I see this quite often when they look at these things for dryers, they talk about the ATEX directive, when really, in most cases, it's the chemical agents directive which needs to be covered there. Now we look at the dangerous substances and explosive atmospheres regulations operating within the UK. We look at the chemical agents directive, and on the left we have health effects, and on the right we have safety. And this means chemical agents directive and ATEX 153 joined together here with cross references to ATEX 114. So on the left, controllers substances hazardous to health assessments, and also the occurrence of asbestos, lead, etc. And on the right, the bit we're interested in, new safety regs, DSEAR, repeal old legislation. Over 70 pieces of legislation were repealed in order to cover everything under DSEAR. Dangerous substances is used instead of hazardous chemical agents because the latter is not defined in British legislation. So the intention of DSEAR, control the risks from substances with flammable, explosive, and oxidizing properties, control the risk from substances which can create flammable atmospheres, and control work activities that could create fires, explosions, or similar energetic events, i.e. thermal runaways. DSEAR also covers you using corrosives and compressed gases. So, how do we apply it? You look at all areas where dangerous substances may be used. Please note there is no minimum amount specified. In other words, they say no matter how small the hazard, you have to look at it and assess it. No minimum process size is defined. So whether you have a pilot plant, laboratory scale, or right up to full manufacturing, you have to consider these. Each one of them has their own hazards and risks. And no minimum number of employees defined. In the UK, we normally have 5 is our cutoff. In Germany, they have more up to 11, and they were fined by the EU for not following ATEX requirements. They had to change it. And all premises should be considered. This could include hotels, shops, storage warehouses, etc. So we'll now have a quick look at background flammability and test data for dusts. 70% of organic powders form flammable atmospheres when dispersed in air. I talked about the Group A test. Group A means flammable, B non-flammable. If the latter, don't worry, you don't have to comply with DSEAR. Look at the properties of the dust cloud only, but also consider dust layers, as these could create fires and become a potential ignition sources. I'm not going to run through them all, but you can see agricultural food, carbons, chemicals, pharmaceutical actives, and incipients, and metal powders. The metal powders give you the massive explosions. Remember, dusts are not homogeneous. If you look up technical literature on it, this is often very old, and I mean very old. It could be 60 years old now. And because you're using your own specific equipment, your own particle size, material can come from different suppliers, the level of humidity, all these things can change the explosion, sensitivity, and violence. Testing is required to understand the flammable characteristics of specific dusts. Try to avoid published literature unless you know you're well within your safety limits. So powder flammability testing. The layer ignition temperature and minimum ignition temperature can look at the effects of temperature on ignition of the dust. Minimum ignition energy looks at the electrostatic spark risk. Maximum pressure, KST, means dust constant. ST is Staub, German for dust, and the Staub class, ST class that it lies in. ST0, ST1, ST2, ST3. Minimum explosive concentration. If you're below that, you don't have a flammability or explosive problem. Limiting oxygen concentration. If you bring it down below there, again, non-flammable. The particle size distribution and the burning behavior. How rapidly does the material burn? Could this spread the fire? In the 1st of January 2021, the EU safety data sheet were changed. I look at it that I'm quite proud that I was one of the people that advocated this change, and I've been advocating it for the last 30 years. If you've got a safety data sheet, it should cover safety data, which includes dust explosion. So now you've got a legal requirement to include data such as MIE, LIT, MIT, PMAX, etc. Lower and upper explosion limits, only the MEC for dust. For gases, flashpoint, auto-ignition temperature for gases and liquids. One of the things I spoke about earlier was hazardous area classification. How often will the material be present and how far out will it come? DSEAR Regulation 7 says places where explosive atmospheres may occur are classified into hazardous and non-hazardous areas. Hazardous areas must be given zonal classification, and Schedule 2 gives the definition of hazardous and the zonal definition. And I'll just run over hazardous. Special precautions are needed to protect the health and safety of workers, and that's the bottom line. Within hazardous areas, special precautions must be applied, and you shouldn't just walk through them unless you're given permission. Area classification assesses the probability of flammable atmospheres occurring. It doesn't tell you how violent the explosion will be. It doesn't tell you how easy it is to ignite the products. It just tells you the probability that flammable atmospheres could occur. Once you've done this, then ignition sources can prevent this. But area classification does not specify the equipment. Area classification doesn't look into consequences. These are part of the general safety considerations. So, five stages of hack. Firstly, obtain data on your products to find out if they are flammable, how easy are they to ignite, and what is the type of explosion violence, and have you got isolation in place? Identify the sources of release. Have you got leaky gaskets? Can they leak through pipework? Have you got isolation or not? Have you got leaking explosion vents or panels? Once you've found out the sources of release, assign the grade of release. Are they most of the time, some of the time, or very, very little? And then assign zonal classification and the extent of the zone. Try to be realistic about the extents and the classifications. Don't overzone. Blanket zoning, I'm not a great lover of this because it's not giving you an idea where the zone 0, 20s are, 20, 21 or 1s, 2s or 22s. So try to stay away from blanket zoning. When you've done it, record, document it, produce drawings, and don't forget the drawings must have an assessment with them, and then review every so often. So the data, MEC, LIT, MIT, etc., powder bulk density, does it fall? Does it float up? Particle size distribution, is it below 500 micron? Do you know the pressure and operating temperatures, the run times, throughput rates, etc. of your equipment? Identify release sources. So you need SOPs, facility plans, P&IDs, process flow sheets, experience operators and site visits. Identify potential release mechanisms. Leakages are quite a common one, and often spillages as well, especially when you're filling the equipment up on areas where you're tipping stations, for instance, or you're adding a liquid or a gas. Is the grade continuous or for long periods or frequently? Does it happen occasionally during normal operation? Or secondary grades not in normal operation, only infrequently and for very short periods? To give you some sort of clue, everybody likes numbers. So here you are. This is for dusts. Continuous, greater than 1,000 hours a year. Can be not a lot. Primary, zone 21s, 10 to 1,000 hours a year. 10 hours a year is not a lot. And secondary is where most of them you want to be in, is less than 10 hours a year, zone 22. So normal operation includes expected abnormal or non-catastrophic events as well. Define the zone and extent. Does fume cupboard type door minimize dust propagation effectively? People leave them open. Do any internal mixing blades cause further dispersion of the dust? Does all powder from rip and tip enter the system, or is it spilt? Is powder spilt when moving sacks from the pallet to the tip point? What rate is the extraction removing powder from the unit? What concentration of dust is likely to be in the ducting? What happens if the extract system isn't on? Will the dust cloud form exterior to the unit? How far will it disperse? Will using multiple powders in one station create issues? Record, document, and review. The drawings have to be to scale, and you have to produce a plan and side elevations. Typical drawings are zone 20, 21, 22 on the right. Notes to accompany the drawings should justification for assign release grades, explanation of why the zones are a certain size, assessment of dust dispersion from all release sources, what engineering measures are in place, ventilation, inerting, etc. What are your operational and maintenance activities, and do you have housekeeping programs in place? Record, document, and review here. So you can see these two drawings, the zones don't change an awful lot. You're lifting up the vessel onto the top to drop down in and to be contained by a screw, moved by a screw conveyor. So here you've got diaphragm valve, hydraulic cylinders, screw conveyor, hopper, drum platform, wall, drum, and floor. So you can see here, even though the equipment, the vessel has been lifted on top, you keep the drawing to be the same for both cases. So review of HACC and associated documentation is required for new installations, during design, installation, and commissioning stages, modifications that you may do to installations or areas, and at a specified frequency. Often I say to people less than 2 years, but you may find that you're very good at housekeeping, you're very good at maintenance, your system hasn't changed in years, and therefore you could increase that review time. Don't forget, if you find any modifications, the drawings have to be changed as well and listed as modification 1, 2, 3, etc. You need signs up to tell where the hazardous area is located. That's the sign there. Put it up where necessary. Don't turn it into an EX Christmas tree. Don't put it when you're entering a room. Put it when you're entering the area, and it must be visible. This provides information for personnel, contractors, and visitors that special precautions are necessary. Now, the basis of safety is the biggest thing we're looking at when we do our report. It's a combination of measures relied upon to ensure safety. It highlights the aspects of the design and operation that's safety critical, and it can be applied to equipment, processes, areas, and work instructions. Building an effective basis of safety, we look at equipment, procedures, operations and mechanical. Deviations from normal, always record them. Human factors, these can be beneficial, they can smell things, hear a change in equipment, and sometimes they can do absolutely total ridiculous things. So try and minimize the effects of humans on your process, and training is very, very important. Material properties, I've been through that. Make sure that you know your properties, your materials. Risk level, how much risk can you tolerate? Can you have explosions on your relief valves going off all the time? If you're in the middle of town, built up area, no. If you're out in the countryside, possibly yes. And many more you may look at and consider to put in your basis of safety. 3 types are normally used for fires and explosions: prevention, achieved by avoiding flammable atmospheres; protection, reduce damage to the plant, stop employees being injured; and avoidance of ignition sources. In other words, prevent sufficient energy occurring. One of the specific risk assessments you may do is non-electrical equipment ignition risk assessments. So as I said before, the main ones are hot surfaces, flames and hot gases, mechanically generated sparks, electrical ignition sources, except for stray currents, and static. This is what we call a non-electrical equipment ignition risk assessment, NIRA. NIRA is used in hazardous areas. If post-2003 equipment is there, you need ATEX certification and equipment protection levels. For pre-2003, this must be proved by doing the risk assessment. Assessment for non-electrical equipment considers multiple ignition sources for each piece of equipment and the level of detail required on the zone in which the equipment is located. Prevent all mechanical sparking, reduce energy less than the MIE of the dust, use slow rotating equipment, look out for trapped metal foreign body, try to prevent this going into your processes, try to use externally mounted bearings and seals, control material feed rates, monitor temperature, have a temperature monitoring sensors on your equipment, and have good maintenance, inspection and lubrication, and good housekeeping. The picture on the right shows scoring a trapped metal when the company told me this couldn't get into the equipment. So equipment protection levels depend on the zone in which it is being used. Zone 0 or 20, safe in normal operation, expected for rare failure. For expected failures and rare major failures modes, this is GA and DA. So gases are GA, dusts are DA. And then we go down to zone 21. This is safe in normal operation and expected failure modes only. These are GB, DB, and the one where you want to be if you're going to zone is zone 2 or 22, which means in safe in normal operation only. And this should read GC, it should read GC and DC. So typical assessment considerations: look at the CE markings, ingress protection ratings, speed of the moving parts, earthing, materials of construction, temperature rise and the rating of the equipment, the emission of sparks, selection of materials to avoid electrostatic charges, avoidance of frictional contact between steel and certain alloys such as aluminium, minimization of leakage of dangerous substances from the equipment, the impact of dust layers on temperature rise, your SOPs, maintenance that you do, the environment that it's operating in. Is it in a hot environment, a cool environment? Is it next door to a piece of equipment that produce leaking gases, for instance? Prevention systems you may have in place, mitigation systems you may have in place. Are you following manufacturer's instructions, and have you installed it all correctly? A typical example here would be rotating blades, the gearbox, hot surfaces for the motor body and bearings, mechanical sparking, contact between the baffles and the casing, friction, impact and grinding sparks, electrostatics, do you have isolated conductors being present? And on that note, we'll move into electrostatic hazards and their control. So in ignition sources by equipment type, you can see static, mechanical, and smoldering. Mechanical is quite a big one here, and you can see a lot of the incidents occur with mechanical, but some are electrostatics. The biggest is mixing, conveying, and sieving. You'll see there for electrostatics. Static occurs wherever movement takes place. It's mentioned explicitly in DSEAR and ATEX, and on the left are a few examples of pouring, coming through pipes, walking, rollers, spraying, and being placed into a mixing vessel, for instance. And all these ones that I showed you there involve movement. It's often intrinsic to the process, so you can't remove it very easily. And it's a very specialized topic. Do not confuse it with electrical problems. It can be used in many places, such as photocopying, surface coating, printing, electrostatic precipitators. It also has many problems. Clinging of products, dust attraction, which stops powder flow, powder segregation. If you've got a mixture of materials and they're charging at different rates, especially in the pharmaceutical industry, this could create problems. And the big ones that you know are nuisance and shock that can happen. The shock may make an operator jump back very quickly, which could be dangerous. He could fall off an upper shelving. And then, of course, we've got ignition, fire, and explosion. So assessment of static hazards, we need to look at the flammable hazard, the flammable atmosphere, how easy it is to ignite it in particular. Can we get charge generation? If we do, can we get accumulation of the charge? How much energy is generated? And what is the discharge mechanism once you've built that quantity of energy up? So, in summarizing, know the directives. Seek expert advice if you're not sure. As a company, we come in and do many ATEX and DSEAR risk assessments and produce the safety folders and reports for them. If you're not sure, then ask somebody, please. Don't make a guess at it. Obtain flammability data on both dusts and powders, gases and vapors. Gases and vapors literature sources are perfectly okay. These don't change very much, and they're perfectly okay to use that. Once you have this data, then determine whether it is necessary to comply with the directives. Perform hazardous area classification. Assess the equipment under ATEX 114 and ensure it is suitable for use for your process, your product. Perform standalone assessments where required. These may mean non-electrical equipment risk assessments and electrostatic detail assessments. Flooring, for instance, shoes, gloves, doing earthing checks on your equipment. And the earthing check should be part of your standard maintenance procedures. Make sure they work. All too often, I see tanks, for instance, with LPG in them, and the earth strap is broken, can't be used or not long enough to be used on somewhere like a tanker or a forklift truck that may be coming near the area. Those earthing checks need to be done as part of the maintenance. Decide a suitable base of safety. Ensure that it is sustainable. And always be aware if any changes are made in the future, then reconfirm the basis of safety is still sound. Write a report summarizing all findings. A report should be detailed enough for people to understand, but try to keep it short enough to make it readable. You can cross-reference other reports that you've done, but try to make it readable. Check at regular intervals and correct if changes have been made. Remember, you can contact us as below for more information, and I hope you found this webinar useful. If you want further information, then get in contact us, and always feel free to either ring or email us to find out more about some information.